Let's look at an example from chapter 12 and let's see how we can use the concept of radiosity and irradiation to calculate heat transfer and rate of temperature change. So let's say we have an aluminium surface or an aluminium block. It's insulated from bottom, and we know that aluminium is shiny, so it will reflect some of the irradiance that's falling on it. So this aluminium, the upper surface of the aluminium has a temperature Ts. There's air flowing at a temperature T infinity and has a convective coefficient of H. G is the irradiance, and the value given for irradiance is 1000 watt per meter square. Some part of this irradiance will be reflected and some of it will be absorbed because we know aluminium is a solid opaque material. The transmissivity will be zero. The temperature T infinity is 30 degrees, H is 40 watt per meter square Kelvin, and we know the dimensions of the aluminium board or the aluminium block. Thickness is 0.05005 meters. The heat capacity of aluminium, I've looked it up and it's 950 joule per kg Kelvin. The density is 2700 kg per meter cube. Emissivity of aluminium is 0.76 and the absorptivity is 0.14, and we need to find what is the radiosity. That means how much radiation is leaving the system or leaving the surface. What is the net radiation? So what is the net radiation in or out of the surface, and what is the rate of temperature change? So we need to find the temperature gradient with time. That's the dt by d time. Okay, so let's see how we'll solve this. So to find radiosity, our equation we know is E. That's the emission due to the surface temperature of aluminium Ts plus whatever is reflected by aluminium. So the portion of radiation that's reflected by aluminium. So our J will be equal to E plus rho R times G. So our emissivity will be will be epsilon times sigma, which is the Stephen Boltzmann constant, times Ts to the power 4. Now, for our next term, we need to know what is or how much of the irradiance is reflected. So we need to know the value of rhos of R. Now we know that the summation of rhos of R plus alpha plus transmissivity is equal to 1, and because transmissivity is equal to 0 as aluminium is opaque, our simple relation will be rhos of R equals 1 minus alpha. So we'll use 1 minus alpha, and because we know the value of alpha is given, so instead of rhos of R we'll use 1 minus alpha times G. So let's substitute the values. Our emissivity is 0.76, Stephen Boltzmann constant 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. Surface temperature of aluminium is 400 Kelvin to the power 4 plus 1 minus alpha. Alpha is 0.14, and the irradiance is given to be 1000 watt per meter square. So this gives us the radiosity to be 1963 watt per meter square. So uh, we are done with part 1. We found out the radiosity or how much radiation is leaving the aluminum surface. Now we need to find out what is the net radiation. So let's say the net radiation in, let's say that the net radiation is coming into the system or coming into aluminum. So we can write this down as Q double prime rad in minus Q double prime rad out. So if our assumption is true, we'll get a positive value. If radiation out is greater than radiation in, we'll get a negative value, which will tell us that our assumption was wrong and the net radiation is going out of the system. Okay, so our Q rad in is nothing but the irradiance G, and our Q rad out is nothing but the radiosity J. So our net radiation will be G minus J. So let's substitute the values. Our G is 1000 watt per meter square minus the radiosity that we just found out is 1963 watt per meter square. And because our radiosity is greater than irradiance, we get our Q net in to be minus 963 watt per meter square, which means that the net radiation is going out of the surface and not in. Okay, so if our Q rad net in is, we can say that it's the Q rad net coming into the system is negative 963 watt per meter square, or we can say that Q rad net going out of the system is positive 963 watt per meter square. Okay, so if you don't want to use the negative sign, you can say that it's going out, or if you want to say if it's that the net radiation is coming in, then you need to include the negative sign. Okay, so now we know what the net radiation is, and we need to find the rate of temperature change. So to do that, we need to apply the energy balance equation. Now remember that we haven't assumed, now if we have to find the temperature change, the rate of temperature change, we cannot assume that the system is at steady state, because that will just take out the time derivative term, so we need that. So our energy equation will have the E dot st term equals to Q in minus Q out plus Q gen. We don't have any Q gen, so our E dot st will be m, that's the mass of aluminium, into Cp specific heat into dt by dt, equals to Qn will be Q double prime rad net in multiplied by the area. So the net radiation that we found out here was a flux. It was in watt per meter square. So we need to multiply by an area here, minus our Q out is heat being transferred out due to convection to the surrounding. So that will be H times A times Ts minus T infinity. Now let's write down our mass as density into volume. So rho is the density of aluminium, and we can write down volume as area into the thickness of density. So rho into A into L will give us the mass of aluminium times the specific heat times dt by dt, and this is the term that we are after in this particular problem. We need to find the rate of temperature change. Okay, so this will be equal to, now that I have written here that the Q radiation is in, that's why I'll include the negative sign. So our Q radiation in will be, and if you see, okay, before we move on to the next step, we see that we have an area term on the right hand side and the left hand side. So our areas will eventually cancel out on both sides. So we don't have to calculate the area separately. So moving on, our Qn is minus 963 watt per meter square minus our heat lost by convection is minus 40 times the temperature difference, that's 400 Kelvin, minus uh, 30 degrees Celsius is around 303 Kelvin. So this gives us, and we'll take the rho into L into Cp to the denominator of the right hand side. So our numerator is 4843 with a negative sign, whole divided by the density of aluminium, the heat capacity of aluminium, which is 950 joule per kg Kelvin, into the thickness of aluminium, which is 0.005, and this gives us the rate of temperature change as minus 0.38 Kelvin per second. So what does this mean? It means that for every second in time, the temperature is dropping by 0.38 Kelvin. If we had got the positive sign here, we would have interpreted this as for every second the temperature is rising by 0.38 Kelvin. But because we have a negative sign, we'll say that the temperature is dropping by 0.38 Kelvin at every second in time, for every second in time. So this is how you tackle with a radiation problem. You need to use these relations carefully and be careful of what sign you are using for Qn and Q out.